In this video now, what we're going to do is we are going to review a few um, miscellaneous methods in sampling. So we've done a rigorous amount of sort of different sampling methodologies. We've done in discrete, we did inverse transformed, then we did accept reject for discrete. And then we also did, some ideas moving into continuous random variables. Now, within continuous random variables, again, we started with inverse transform. Again, we did accept, reject. But then within continuous random variables, we also dived into the ideas of trying to implement Box-Mueller methodology, particularly for the Gaussian distribution. And we've just ended with ratio of uniforms, right? So we've done a few different methodologies. Now there's another one that's actually really useful and helpful in trying to generate samples. And that is the idea that you can use known relationships between random variables. Okay. A perfect example of this, and I'll go through a series of examples, but a perfect example of this is let's consider the binomial distribution. Now we know that if y1, y2 up to yn are IID Bernoulli random variables with probability of success p, and I construct x to be equal to y1 plus y2 plus going up till yn, then this new random variable x is distributed according to binomial n comma p. What we can do is we can actually use this methodology to generate samples from binomial n comma p. We've already learned how to generate Bernoulli random variables. So if we simulate n Bernoulli random variables, independent, and each of them having probability of success p, okay, and we add them up, okay, we add each of those random variables up, whatever we see from them, then what we have is exactly a realization from a binomial n comma p random variable. Okay. And so these are the types of distributions, relations between distributions that we can use to generate samples. There's multiple other such relationships. So let's look at another one, the popular negative binomial distribution. Now the negative binomial distribution is the number of failures until the rth success. Okay, so how many times have we failed in some trials until we have the rth success? So this sounds like some geometric random variable, right? And that's exactly very similar to a geometric. And as it turns out that if we have y1, y2 up to yr, okay, which r is the rth success r, right? These are all distributed according to the geometric p. Okay, geometric p meaning how, and this is which geometric? Because there are two geometrics, one that counts the number of trials and one that counts the number of failures. I'm talking about the one that counts the number of failures. So if I take y1 up to yr, IID geometric random variables which have probability of success p, and then I add all of them up, and that random variable x is exactly a draw from my negative binomial with parameters r and p. We've already discussed a little bit on how to generate geometric random variables, and so we can use this to actually generate negative binomial random variables as well. Okay. Similarly, let's think about the beta distribution. If x follows gamma a comma 1, and there's something missing here, and independently, okay, so x and y shouldn't have any dependence. So if they're independent, x follows gamma a comma 1 and y follows gamma b comma 1. Okay, then the ratio x by x plus y is a draw from beta a comma b. And similarly, actually, y comma x plus y, you can imagine, is a draw from beta b comma a. Okay, and we can use this relationship to actually draw beta random variables. All right, let's look at another one, the Dirichlet distribution. The Dirichlet distribution actually is a generalization of the beta distribution. So the Dirichlet distribution has a probability mass function, which is that f of x1, x2 up till xk. So the Dirichlet distribution is essentially k-dimensional. It's not a one-dimensional random variable like beta, binomial, negative binomial, and so on. In fact, it is k or also k minus one dimensional, but let's just stick with k. The reason is that what you actually get is if you draw a value from this PMF, you're going to actually get k values because it's k dimensional. And the probability mass function of all those values is given some given some parameter alpha. So these are fixed constants. Given some parameter alpha, the PMF is this constant value times the product of xi to the power alpha I minus 1, where the support of the xi's are all positive. Every xi, I going from 1 to k, is positive, but also they have to all add up to 1. Right? This is the Dirichlet distribution PMF. But this turns out to be a generalization of a beta distribution in the sense that to get a draw from such a Dirichlet, if we have independent gamma draws y1 up to yk, k again being the dimension, such that the shape parameters are alpha 1, alpha 2 up until alpha k, and the rate parameters are just 1. Then if I set xi to be the yi divided by sum of yi, right? Again here, I going from 1 till k. And if I take all those x1, x2 up to xk, all of those vectors, right? They have to add up to 1 because this ratio, when you sum over all I, has to add up to 1, right? Then this is actually going to be a draw exactly from a Dirichlet with this PMF. This is a generalization of the beta distribution. There's more relationships. For example, a chi-square distribution. If y1, y2 up to yk are distributed IID normal 0, 1, right? Then if I sum a square and sum all of these y random variables, y1 squared plus y2 squared up to yk squared, add all of them up, call that a random variable x, then x will be distributed according to a chi-squared distribution with k degrees of freedom. So if the degrees of freedom k is an integer, it need not be. If it is an integer, then you can easily simulate from this using this methodology. Okay, the relationships don't end there. We can do the same thing for t distributions. If z follows normal 0, 1 and y is a chi-squared k random variable and these two are independent of each other, then x equals z divided by square root y by k. This sort of complicated looking setup is distributed as a t distribution with k degrees of freedom. Okay, hopefully you've already seen, if not all, but most of these distributions. So that's a sort of quick summary of all the known relationships between some of the more popular distributions that you can actually use to generate random variables. Okay. Now, similarly, we also have another popular feature of distributions that can be used to actually generate random variables, and that is that some distributions are from what you call a location scale family, which means that if f is a distribution in the location scale family, then z, a random variable z, has a CDF fz, f sub z, small z, in the sense that it doesn't have any parameters, right? So let's say you have a random variable z, has a CDF fz, in the sense that it doesn't have any unknown parameters. Okay, there's nothing, no more information you need to understand the distribution function of z. Then for mu in some r and sigma that's positive, if I define a new random variable y equals mu plus sigma z, then this new random variable has a distribution f of z y minus mu minus sigma by sigma. So f of y at y is nothing but f of z at evaluated at a different point, at a centered and scaled point. And with that same logic, if Z has PDF f of Z, then this Y has PDF this. Okay. Why is this useful? Well, it's useful in the sense that if Z follows normal 0, 1, okay, then Y plus mu plus sigma Z is going to follow normal mu comma sigma squared, right? So we've learned many methods to generate standard normal random variables, but we've only learned the ratio of uniforms to generate any normal random variable. So for accept, reject, and Box-Muller, if I can generate standard normals, then all I need to generate a different normal is to just scale it and center it. That's all. Okay. So this is one of the main things in um, trying to understand known relationships, is that we can understand how different random variables are related to one another in order to be able to generate these random variables. Now, another methodology. So we're just going over some miscellaneous methods in getting samples. Another one specifically is sampling from a mixture distribution, and this one's important, particularly later on when we get to something called the EM algorithm. It's going to come into handy to go over this a little bit more carefully. Okay. So now we're going to learn about, the next thing we're going to learn about is sampling from mixture distributions. Something we've done a little bit in the discrete case using composition. And we're going to do this again in a slightly different way, because we're going to do it for continuous random variables as well. Right? So composition and mixture distributions for continuous densities again are very similar to the discrete distributions that we've done previously. Now for J going from 1 through K, where K is going to be the number of mixtures we have, let fjx be a distribution function, and small fjx is going to be its corresponding density function. Now a mixture distribution function, capital F, the combined sort of final distribution, is going to be f of x equals summation j going from 1 through k pi j fjx, where the pi j's are all greater than 0 and have to add up to 1. Okay, this is the idea. And we've done this before, again, in a similar form, but we did it for discrete random variables. Now the corresponding density is f of x equals summation j going from 1 to k pi j fjx. And the way to sample from this is very similar to the discrete case, is we draw for each fj, if we can draw from each of the singular fj's, then in the same way that we did in the previous discrete case, we will be able to draw from the mixture distribution capital F as well, using the same exact steps. Those steps are the following. First, you generate our favorite uniform random variable. If u is less than pi 1, then you generate from f1. If it's less than pi 1 plus pi 2, you generate from f2. If it's less than summation pi I going from 1 to k minus 1, you generate from fk minus 1. And then finally, if none of these happen, then you finally just generate from fk. Okay, so let's actually look at an example of what a mixture distribution looks like that's actually practical and useful. So our first example is that of mixture of normals. So consider two normal distributions, normal mu1 sigma 1 squared and normal mu2, sorry, this should be mu2 sigma 2 squared. Now for some p between 0 and 1, right? So this p corresponds to our pi's before. We had chosen pi 1, pi 2 up to pi k before, because there can be multiple components. But now, because we're only going to be doing a two component mixture in this case, we're just calling it p. Now the density, the mixture density is f of x is p times small f1 x mu1 sigma 1 squared plus 1 minus p f2 x of mu2 sigma 2 squared. Now what does this actually look like? Well, I can just plug in what f1 and f2 are. F1 and f2 are the corresponding densities of the individual Gaussians. Right? So this is p times the first Gaussian, the density of the first Gaussian, and 1 minus p times the density of the second Gaussian. Okay? The way this is helpful is we can have, let's say this is my real line, and I have one distribution over here that looks like this, and my second component also looks something like this. So roughly speaking, this is my mu1 and this is my mu2. Okay, and roughly speaking, this about this length is my sigma 1 and about this length is my sigma 2, roughly. So based on the values of p1 p mu1 mu2 and sigma 1 sigma 2, we can get various shapes of the distribution. For example, oops, we could also get something like this. We could get something like this. We could also get something like, right, something like this. Okay, and it can take as many shapes and forms really that you can imagine when you take two curves and you just mix them into each other or you separate them out. Now we can think of an example also where this is relevant. For example, let's say I'm thinking about number of runs made by a player, or not number of runs, but let's say the average, batting average. Yeah, let's go with that. Batting average of a player. Let's try that again. So let's say I look at batting average of all players in the Indian cricket team. Okay, and you can choose a particular format, right? So if I look at the batting average of all players in the Indian cricket team, I might expect something that looks like this, right? The blue one. I'll expect the batters to have a reasonably high batting average. If it's ODIs, one day internationals, it's maybe around 40. And I'll expect the the bowlers to have a batting average relatively lower, somewhere around 20 or 15, right? So the batting average of all the players can have a distribution that's sort of quite separated in bimodal, right? And there's various other examples. Eventually, what we'll do is we'll actually look at fitting mixture distributions for clustering problems. We'll actually look at this for different variety of different data sets. So this will come in handy. How do you sample from a Gaussian? Well, same idea. You generate a uniform. If U is less than equal to P, then you generate from the first Gaussian. And this you can generate using the location scale family trick that we've discussed. Otherwise, you generate from the second Gaussian. Okay. This is one example of a mixture distribution. Again, we can look at a few other examples. So another one that's actually quite interesting is because it is going to be a mixture of a discrete random variable and a continuous random variable. Okay. This is the zero-inflated gamma distribution example. Now, just like the zero-inflated Poisson distribution, we can also think of a zero-inflated normal or a zero-inflated gamma. Let's motivate a zero-inflated gamma distribution. Suppose you are an auto insurance company owner, or you're an auto insurance company, and you want to study the cost of claims associated with each customer. So, customers have vehicles, have cars, and when they buy a car, they will also get car insurance. Okay. And when there's car insurance, there's also claims for the car insurance that, okay, somebody got into an accident and filed a claim so that they can actually get some insurance money back for whatever monthly that they've been paying. Right? So that is each customer, if they have an accident, will come to you and claim insurance money reimbursement for that accident. So let X be equal to the insurance money asked for by a customer in a month. Right? So you have the company has various customers, and X is the random variable that is the insurance money that has been asked for by a certain customer, by customers in a month. However, most customers hopefully will not enter into any accidents in that month, right? Most people don't have random accidents every day. So they're going to claim rupees 0. They're not going to claim anything. But when there will be customers making a claim, they will claim reimbursement for some amount of money that, let's say, follows a gamma distribution. Okay. So when there is an accident where they do get into an accident, then they will ask for some amount of money for reimbursement that may follow some distribution, let's say a gamma distribution, because on the positive real line, it could be any number. It could be 10 rupees, it could be 10,000 rupees, it could be 5,295 rupees. So the density function for this can be thought of as a mixture between the gamma distribution and the zero random variable, the random variable that takes mass at zero. So we take P portion of the mass and we give it to zero, right? Plus 1 minus P times the random variable, the gamma random, the density of the gamma random variable. Right? Sampling from such a zero-inflated gamma is generate a uniform draw. If u is less than equal to p, then return x equals 0. That means if with probability p, I will not have any claims. So p can be probably very large. Otherwise, generate x from gamma alpha beta, where alpha beta are going to be something pertaining to the problem. Okay. So in this way, we can also use the idea of mixture distributions to actually really understand and study a particular type of data set or a particular type of problem that we are faced with. They actually are very useful in modeling different objects and things. All right. We're almost done with our sampling. We have one topic left, and that's going to be the next video, which will talk about multi-dimensional targets. And then once we're done with that video, we actually go into what do you do with these samples that we've been learning how to generate. So very soon we're gonna get into what are you going to do with some of these samples as well.